Share screen. Okay. Okay, so Assalamualaikum warahmatullahi taala wabarakatuh. Today we will continue with our last lecture in week 13. So your final exam will be on 2nd July on Friday at 3 p.m. Okay, so for the last lecture here, we will continue about the invertible and non-invertible measure preserving transformation, and then we will consider how to calculate the invertible and non-invertible entropy. Okay, first, let us consider the entropy of measure preserving transformation. Okay, so you will have the measure space. So in the measure space, you have the measure of all, or the whole X must be equals to 1. Okay, so the first property is that you must have the finite partition. Okay, and you know the formula to get the entropy, to calculate the entropy, is given by this formula. AI log mu AI. Okay, and the second one, you have the relative entropy, or we could say the entropy of the measure preserving transformation T with respect to the partition psi. So we have the relative entropy is given by this limit. So the limit from n goes to infinity of the entropy of the joint partition over n, or we could say 1 over n. Okay. So for these two properties, this is invertible. Invertible meaning you can find the inverse. Okay. Now for the third property, we have entropy of the T, or the transformation. So we have, it is given by the Kolmogorov-Sinai. Stated this is equal to the supremum of the relative entropy. So we find the supremum of the set of the relative property, where psi here is the finite partition. Okay. For example, from these three properties, so I have X is finite. So if X is finite, and you found already what is the entropy of T, right? In previous calculation, you got this 0. So if X is finite, you have the entropy is equals to 0. So this means that your T is invertible, because you can find the T inverse too. T inverse 1, T inverse 2, T inverse 3, and so on. Okay. So kalau you can find the T inverse, that means your T is invertible. Okay, now for number 2, let's consider this set. Okay, so M is a usual Lebesgue measure, and you have the Ariadic transformation is given by this formula. Tx is equals to Rx mod 1. So here we consider R greater or equals to 2. So how can you find T? T inverse. So you found T inverse, right? T inverse minus 1. So for the case of 0, 1, if you remember, in our previous calculation, if psi is, let's say you got 2 elements here, so your T inverse psi will have 4, right?
Yes.
So
Yes.
if in this case, to be invertible, memang you can find the pre-image, okay? But the number of the pre-image is greater now. So from this here, from this object, you got the pre-image is 2. The unit the pre-image is 2. So this is non-invertible, because kalau invertible, you go to that point and then you can go back to that original point. Dia tak boleh pecah jadi 2 and then jadi combine jadi 1. Cannot. So kalau invertible, maksud dia pergi A to B, B can go back to A. Dia one to one. Dia kena one to one. Okay. So for this case, this is non-invertible because you could have how many R pre-images? I mean how many pre-images? Kalau R, maksudnya you will have R pre-images. So we can find the R pre-images. So if you find the entropy, this is R log. This gives you log R. Okay. For example, so this. Okay. So because H of T is log R, and you found this, right? You can have a finite partition where AI is given by this. Every element here can be written as this set I minus 1 over R to I plus 1 over R. Okay, that is for number 2. Now example number 3. Okay, so I have if E is Bernoulli shift 0, 1, 2, where the measure, each measure is given by this Pi. So kalau V0, P0, V1, P1 and so on. And the summation of all the measure must be 1. Okay, and I have the coordinate function, partition function EI, where EI is equals to E. So for any I runs from 0 until infinity. So I have psi. So in Bernoulli, you can define your element of the partition to be the first coordinate to be 0. Or the first coordinate to be 1. So for the case of kalau D2, kalau psi is R minus 1, so that means you can define until R place equals to R minus 1. Okay. So T is the Bernoulli shift, we know, because we define it to be Bernoulli shift. So you found that in previous calculation, the entropy of the Bernoulli shift is what? by this formula, right? Minus you have minus sum until r minus 1 pi log pi. So if you look at this example of Bernoulli shift, if you find the pre-image of the partition, so what is the pre-image of the partition? How many?
R minus 1.
Yes, R. Sebab kosong sampai R minus 1 is R. Total dia ada R. Kan? So you will have R pre-images. So in this case, your T here is non-invertible. Okay, so another example. So this one is for Bernoulli shift with one-sided. I mean, dia sebelah kanan saja, positif. So for the set of this one, so if you have tilde, that means that is for the partition function of from minus infinity to infinity. So again for Bernoulli shift, but for double-sided. So how can you find? For the double-sided case, also the same, you can define this one for until R. First digit is 0. And the second digit, the first digit is 1 until the first digit is R minus 1. Okay, so you can define omega. So since this is a double-sided, so you can start from minus, right? So you can have omega minus 2, omega minus 1, omega 0, omega 1, omega 2 until omega 3 and so on. Okay, so this is the position for 0. This is position of 1, 2, 3, and this is minus 1, minus 2, and so on. Okay. So can you find the image of the omega? First, try to find T omega. What do you have? It's like you shifting, right? Because this is Bernoulli shift in two-sided. You shift.
Yes.
So what happens? So when you shift, this is the same. Omega minus 2, omega minus 1, omega 0, omega 1, omega 2, omega 3. So when you shift, the position of 0 and omega 0 ni becomes, so 0 ni dekat mana pula? Dekat minus
1.
Okay, 0 dekat minus 1. So that means you shift, that means you cancel. Macam you cancel dekat tempat omega 0. So omega 0 now become in the first place here, right? Is that okay? Sorry. Omega 1, 0, sorry. Terbalik. So omega 1 should be 0. Omega 0 will be minus 1. Correct? Minus 2. You shift. You bring, you shift kan?
Betul.
Betul. So omega 1 become at the zeros place, omega 1 at the minus 1 place become omega 0. You shift to the left. So minus 1 kat situ. And how can you find the pre-image? So now pre-image T So what happens to the pre-image? So I have omega 2, the same, omega 1, omega 0, omega 1, omega 2. So now the place. So the place of when you shift, this one become omega minus 2 become minus, the place of minus 1. Omega minus 1 become 0. Omega 0 is 1, 2, 3 and so on.
Bukan
Pre-image.
Dia bukan patah balik jadi W juga ada. Jadi omega.
Macam mana?
Bukan.
Dia kalau tengok, kalau image you go shifting kan ni. This one from omega you got T omega. So kalau pre-image from omega here, you look at T inverse. So you inverse. Faham tak? You inverse from omega. Okay, from omega you start with omega. Apa-apa start with omega. Either you go to the right, either you go to the left. Shifting to the right, shifting to the left. Boleh. So kalau T omega, that means you macam shift to the right. Betul tak? You bring everything, you bring T omega cancel, sorry. T omega you shift to the, you shift this thing to the right. Kalau T omega you shift the red one to the right. If T inverse, okay, if T inverse you shift to the left. You shift the red, the values, the position on the red, shift to the left. Boleh?
Boleh. Kalau tambah satu elemen kan?
Ya. Kalau pre-image kita macam patah balik satu elemen, kita tambah, kita adding. Kalau T omega kita buang satu elemen. So position ni dalam red kan? Okay, dan yang saya bulatkan dalam merah ni maksudnya perjalanan dia. So kalau T omega kita shift to the right, so kita bawa, kita pindah satu to the right. So on the 0 akan jadi minus 1 sebab kita bawa ini ke sini. Okay, for the case of pre-image, you shift to the left. So that means your 0th position ni dekat belah kiri, dekat kawasan ni. Okay. Boleh nampak? Alright. Okay, good. So kalau using this, the double-sided sequence, now kalau you want to find the relative entropy, okay, so I have, according to the definition, this is equals to limit of 1 over n of the omega joint, right? But for our case, kita dah ada finite, betul? Kita consider finite case. So if we consider finite joint here, so I have from minus n to n. Betul tak? So if you consider minus 1 sampai 1, so you will have how many elements? 1, 2, 3. Okay? Sebab kita include 0 kat tengah tu. Kalau kita consider between minus 2 to 2, so how many do you have? The elements summation. So you should consider minus 2, minus 1, 0, 1 and 2. So you will have 5. So the limit of relative entropy for the double-sided case we have the limit of 1 over n multiplied with the entropy of the join of the pre-image of this. This is not n anymore, but becomes, so if n 1, you will have 3. If n is 3, so n is 2, you will have 5. N is 3, you have 10, right? So this is the general, so to get the limit, so you have 1 over 2n plus 1. Lucu. 7, not 10. Okay. So for the case untuk n yang sebelum-sebelum ni, kita guna finite, tapi kita guna hanya sebelah side je. If you remember. So for the case of, kalau for the case of double-sided, we have 2n plus 1. Plus 1 ni sebab dia consider ada 0 kat tengah tu. Another extra position. So in this case, I have from previous calculation, you can check your calculation in previous lectures. So I have T pre-image of the partition x1 omega equals to 0 until x 0 until x1 omega r minus 1. Okay, so the pre-image of psi is given by this formula. And the T of psi becomes x minus 1 omega from the previous position that you found already, this one. Kalau T omega or T psi, you will have 1. Position of 0 start with 1. So I have x1 lah, x1 omega. That's why you write here is x1 omega. Kalau and then you find the T psi here is T inverse T psi tadi. So T inverse, you got this one, sorry. This one. Sekejap. T inverse dulu, okay. T inverse, so you refer to T inverse of omega. So for the case of omega 0, becomes 1, the position, x1. So here you have, in the element, so you have x1 omega equals to 0. And so on until x1 omega equals to r minus 1. So for T psi, you refer to the T of omega. So T of omega, this one. So your 0 now become minus 1. Position of minus 1. So therefore, you have x minus 1 omega. You faham tak? Any questions this part? Tak faham kat mana? Faham, okay. So kat sini teruskan, okay. I continue. So I have this one equals to 0 until x minus 1 omega equals to r minus 1. Okay. Now let's try to take the join of this partition. So I have the pre-image of psi join with psi join with T of psi. So just to recall that your psi just now is x0 omega equals to 0 until x0 omega equals to r minus 1. Okay. So by joining, so how to get join? I think you should remember you have to find the intersection, betul? Join of this, you have to consider all the possible intersections in the elements. So what you should get this is equals to minus 1 until 1 T inverse I of psi, which is equals to x minus 1 omega is equals to I minus 1. X 0 omega is equals to I0 and x1 omega equals to I1. So you should get three elements in this partition join partition. Okay. So now you can find the entropy. You can try to find the entropy. So for the entropy of this, H of this is equals to what? Agak-agak berapa?
3.
Yes. 3 ke berapa? So for the joint partition dia kan ada tu 3.
3. Oh.
Boleh?
Okay.
So check baliklah calculation in the previous lecture. So you will get 3 of multiply with a multiple of 3 of the entropy of the partition. Okay. Dan sebelum ni kan kita kira ada dapat 2H psi. So since we join with 3, right? 3 partitions. So you must have 3 multiple of this. And you got 3 elements. Now generalization. Okay, another. So if you do more, let's say you have this I2 minus 2 to 2 V. So if you have I2 minus 2 to 2 of the reimage of the double-sided, so you should get how many elements? So kalau minus 2, you start with minus 2. Yes, correct. You should get this one, I minus 2. And then x minus 1 is equals to I minus 1. And then x0 omega is I0. And then x1 omega is I1. And x2 omega is I2. So you should get these 5 elements. So by finding the entropy here, T inverse of psi, you should get how many?
5.
5H psi. Okay? This one. So you can try by yourself. Boleh carilah satu-satu kalau rajin. Or you can just cari macam ni. This one. Okay, so for conclusion, for this example, conclusion. For invertible Bernoulli shift, for invertible Bernoulli shift, we have the entropy of the invertible Bernoulli sheaf and the entropy of the non-invertible Bernoulli sheaf. Actually, they are the same. Entropy. So if they are the same, then we can say that our psi here is the generator. So if they have the same entropy, then we can say that our psi is the generator. So if you still remember the definition of generator, kalau saya tak tunjuk ni. Oh tak, betul. Ingat saya tertinggal ni tadi. So kalau maksud generator, kalau if you get the entropy, generator meaning that HT is equals to HT of psi. Psi is the generator. So kalau relative entropy and the entropy of T is the same, then you can conclude that your psi is the generator. So kalau pakai generator, now you can use Kolmogorov-Sinai lah. After that, you can find the supremum. Nak cari HT. Okay. How to find the Kolmogorov-Sinai? Let me check. Let me continue. Okay. So now I can use Kolmogorov-Sinai theorem for invertible Bernoulli sheaf, as in example number 4 or property number 4 just now. I have H of T is equals to H of psi, which is given by this formula. EI log EI. Okay, so your entropy of the transformation is given by this formula. And you found already if kalau uniform, kalau tak uniform, so you should see. Kalau uniform, you should get something. What is the value? Kalau dia tak uniform, you should get something. So kalau uniform, dia dapat berapa? Log R lah. Betul tak? So if uniform maksudnya Pi is equals to 1 over R. Okay. So then H of T is log R. So kalau tak uniform, maksudnya ada satu yang different. So you should get, you should use the general formula. Then find HT is given by this. Inilah. Okay. Find manually lah. Any questions this part?
Tak ada.
Okay, alright. Okay, kita move on to another example. So in the previous lecture number 8, so you show that already Baker's is isomorphic kan? Okay, let assume that you show already that Baker's is isomorphic with the Bernoulli shift. Bernoulli shift for R greater or equals to 2. Again, I recall. So your x star, your x tilde should be from 0, 1 until 0, 1. This is because we consider Becker. Becker, we have x and y coordinates. So bxy or the Becker's transformation is given by this. Is defined to be by this formula. So 2x half y, 2x minus 1 and half y plus 1. Okay. So here for the case of x is between 0 to half. Another one is half, x is between half and 1. Okay. So how can you find bxy? B inverse, the pre-image of xy. Actually, you can find by this way lah. Sama ada you can find b inverse of xy is equals to, macam mana nak cari inverse of 2x?
1 over 2x.
Okay, 1 over 2x. So for y dapat berapa?
2y.
2y, correct. So this one akan jadi in terms of x kat sini akan jadi in terms of y dekat sini. Okay, kita macam balikkan dekat kita project our graph tu kepada y axis. Now for the case of second case, you will have half of x plus 1. Another one would be 2y minus 1. Half. Boleh?
Boleh.
Okay. So how to check whether your B inverse is correct or not? You should check by this lah. B xy, find the composition. Compose with B inverse of xy, you should get the same identity. You should get xy lah. Or you can check using by or B inverse xy composite with B of xy. You should get the identity. So check lah kalau you choose any numbers, x tu berapa, y tu berapa, try to put in your composition function and then you can get xy. Kalau sama maksudnya your inverse is correct. Okay, so if that happens, let's say you show that this is correct. Let's say your B inverse is correct, pre-image, okay? Inverse B, so after verifying, let us assume is verified. Okay, so we could say what? We can say, we say that B Baker's transformation is So if you get, if you from 1 point to 1 point, you can get back your the original point. So you can say that this is invertible. So for every case, you should get 1 point, go to 1 point, and then come back to 1 point. Dia takkan ada many pre-images. You should get one image goes to one pre-image. So we say that Becker's transformation is invertible. Okay, so we know already that your Becker's and Bernoulli shift is isomorphic. So you will have x to x, x tilde to x tilde for Bernoulli shift. So we apply Becker's, and then another one for the omega tilde to omega tilde, we apply Bernoulli shift T. So T tilde is for the double-sided product. Again, so I have 0, 1, V, 0, V. So I would say T here is Bernoulli shift of two-sided. So your function here, your map here, you from x tilde you can bring to omega tilde, right? Because this is, kalau isomorphic, this is the commutative diagram that you can have. So either you can go this way or this way. Itu je. Okay, so that means you want to start from the Becker's to go to the omega tilde. So how can you write this function? You can write in terms of this. So I have double-sided, right? So I have x1. So your here 0, x1, x2, this is the function. This is your Becker's. So if you have x, y, so that means you can write 0 point x1, x2, x3, and so on. Okay. So now we want to create a one-to-one correspondence between these two. So I have so for the first 0th position, warna lain. So 0, 1, 2, 3 until -1, -2, -3 until so on. So okay. So from the previous map here, function here, coordinate function, 0 point x1, x2, x3, right? But this one, sorry, ada y. So another one is 0 point y1, y2, sebab ni double sided. Boleh? Okay, so xy, remember, so on the right side would be x1, x2, x3, x4. So this is a positive side, and the left hand side, which is the position of y. So y1, y2, y3, and so on. Okay, so this is for the one-to-one correspondence. So this is so from Becker's, from the Bernoulli double-sided, you got this. Becker's is isomorphic. So you shown already in the previous class. Becker's is isomorphic to T tilde, which is the Bernoulli shift with R equals to 2. So this gives you your measure is 1/2. So if T tilde have the same entropy, so if Bernoulli shift give you what entropy? So you can find Bernoulli shift punya entropy because dekat sebelum ni saya dah tunjuk. So H of T tilde is using the general formula, right? And see that this is apa? Uniform. So kalau uniform, actually you can directly use, you can directly see that it is log 2. But I can count. I can use the general formula lah. Sekejap. I have this I equals to 0 until 1. So I have Pi log Pi.
Negatif ada tu.
Yes, negative. Zero until 1. Okay, so I have P. So Pi is 1/2, right? So minus P0. You will have minus P0 log P0 minus P1 log P1. So minus P0 is actually mu 0 ni lah. 1/2. So you have minus 1/2 log 1/2 minus 1/2 log 1/2. So you can simplify. Here minus 1/2 log 1 minus log 2 minus 1/2 log 1 minus log 2. Simplify and then you get this is equals to log 2. Boleh?
Boleh.
Okay, so now since you got the entropy of the Bernoulli shift is log 2, so and you have found that Beckers is isomorphic to Bernoulli shift, so what is the entropy of the Beckers?
Log 2.
Yeah? Log 2, okay. Correct. So that means entropy of B here is log 2. So kalau isomorphic, that means they have the same property. If you know one of the property in the one of the transformation, let's say Bernoulli shift, you know, you found already all the entropies, relative entropy apa semua, so maksudnya they have the same value. So tak payah cari untuk Beckers lagi dah. You just find the statement that since Beckers and Bernoulli shift is isomorphic, therefore they have the same entropy. In this case, since our H T bar is T tilde is log 2, therefore our H of B or the entropy of the Beckers is also log 2. Statement habis. Okay.
Memang tak ada formula lah untuk relative entropy Beckers ni.
Tak, dia senang sebab antara Bernoulli shift and Beckers, the easiest way to find the entropy is using Bernoulli shift. Sebab tu kalau usually in dynamical system, kita nak isomorphic kan, kita nak cari relation dengan transformation lain sebab kita nak cari analisis yang paling senang. So kalau Bernoulli shift tu kita dah ada segala information dalam tu, kita maksudnya nak cari entropi dia pun boleh lah, senang je lah kan, kita boleh cari. So bila dapat cari satu property yang sama, kita relatekan dengan another transformation, so therefore tak payah cari dah lah yang dalam Beckers yang mungkin complicated lah, ada dua, kena consider dua cases lah, kena consider nanti partition lain lah, partition dalam case tu, partition dalam case ni. So macam agak confusing kan. So better cara dia adalah senang, isomorphic, cari benda yang isomorphic. So since they are isomorphic, they have the same property, boleh relatekan je. So tak payah cari yang susah, cari yang senang. Macam tu. Okay.
Okay.
Alright. Do we have time? Okay, actually we have. Okay, so I think we write another conclusion. Last one. So let's state some important statement. So for non-invertible case, okay, we cannot find the image TA. Say, for example, if you want to find the image of but we can find the pre-image of X omega 1. Kalau invertible case, for non-invertible case, kalau you have this part, right? You have this X0 omega equals to 1. You cannot find the image of this element of A. Sebab apa? Kita tak tahu apa itu next. Kalau dia bagi ini je, kita tak tahu apa next point dia. Betul tak?
Betul.
But we know we can find the inverse. Sebab inverse tu already maksudnya kita dah kita shift. Bila kita shift, dia ada information about the previous element. So that's why we can find the pre-image. So kalau image tak boleh sampai tapi pre-image boleh dapat, so we say that is a non-invertible case. So kalau for invertible case, we can find everything. Sama ada image or pre-images. So dekat mana-mana pun for invertible case, dekat mana-mana point you start, you can find from the previous point dengan the next point. Okay, and the same apply for the dyadic case to X mod 1. You should get entropy of T, entropy of the dyadic is log 2. Sebab apa? For dyadic you show already that it is isomorphic with Beckers. Ke tak? So actually you can show that our dyadic function, our dyadic transformation is also isomorphic with the Beckers. So since they are isomorphic, then we can say that our entropy of Beckers is also log 2. Ni another example lah ni. Okay.
Bernoulli shift tu dyadic
Bernoulli shift? Tak, Bernoulli shift bukan dyadic. Bernoulli shift tu yang mana? Yang Bernoulli shift kan ada dua. Satu double side, satu one side.
Dan omega tilde isomorphic dengan Beckers kan?
Yes. Yes.
Dyadic pun isomorphic dengan Beckers juga?
Yes, actually. Tapi saya rasa kita tak show dalam kelas. You just know je lah. You know that dyadic ni isomorphic dengan Beckers. For previous class, we show dyadic dengan Bernoulli shift, betul tak?
Kita show
For isomorphic case in lecture 8, first kita show dyadic dengan Bernoulli, yes. Tapi itu Bernoulli yang one sided, which is on the positive side je, dia tak ada Y.
Oh, Bernoulli dengan
diadik. Lepas tu sebenarnya Bernoulli diadik dengan Becker pun isomorphic juga. Cuma tak ada dalam example, saya tak show. Lepas tu kita consider isomorphic Beckers dengan Bernoulli shift yang double sided, which mean the Bernoulli shift yang apa, ada tilde tu lah. And in fact we know already our Beckers is isomorphic with Bernoulli shift of double sided. So kita akan dapat entropi diorang sama. Okay, so ni another statement for extra remark. Untuk case diadik dengan Beckers, actually they are isomorphic and thus you can find that they have the same entropy. So better to find the entropy of diadik daripada to find entropy of Beckers. Betul tak? Sebab diadik ni kita dah cari sebelum-sebelum ni. Entropy dia berapa. Tu je dia nak tambah. Okay.
Okay.
Alright. Okay, so I think that's all for today's class. Any questions before we end our class?
Doktor, yang omega tidak tu invertible ke tak Non-invertible kan? Yang double
Invertible.
sided punya.
Invertible kan?
Invertible.
Invert. Sebab dia ada one to one correspondent ni. Dia ni. Dia boleh invertible. Invertible meaning you can find image, you can find the pre-image.
Dia sebab omega asal tu dah tahu kan semua points ni.
Yes. Omega asal tu dia kan ada position. So dia tak kisahlah apa values yang dekat position tu, as long as you know already. Betul tak? You know all. Double sided meaning you can fix all 0-1 dalam your sequence. So infinitely many, so that means you can fix infinitely many position. So either you shift to the right or you shift to the left. Tu je. So since if you shift to the right, you know already what is the previous element sebelum, and then you know what is the previous after you shift. So actually yang invertible kat case ni adalah Bernoulli shift with double sided. Yang sebelum ni kalau ada Bernoulli shift yang ada R pre-images tu, so tu tak boleh jadi invertible sebab dia ada banyak. So you don't know which one that can bring you, kalau you cari pre-images, okay, you can find the pre-images but you cannot find the next point because you don't know what is the next point, betul tak? Dia dah cancel lah kat situ. Macam tu. Okay. So for conclusion, for the case of X is finite, let's say any transformation ABC ergodic ke apa, so kalau dia punya entropy here is 0, so we say that it is invertible. T tu invertible. For another case, kalau kita consider in 0-1 segment, in previously we know psi, we can find the pre-image, right? Okay, so pre-image ni tak sama. Sebab you don't know, sebab apa tak boleh dapat? Sebab you don't know which goes to where, for example. So this is non-invertible because you will have R pre-images. So for the case of one-sided, this one for number 3, for one-sided also you cannot find because you could have pre-images dia adalah R pre-images. So this is T also non-invertible. So for the case of tilde, dia invertible. Sebab apa? Sebab case ni lah you can find omega, T omega and also T inverse omega. So to find the relative entropy, dia ada extra plus 1 here, extra position. So that's why you can change kat sini je lah. Okay. Only invertible case only for the double-sided Bernoulli shift. Just remember that one. Okay, any more questions?
Tak ada.
Alright. Okay. So if not, then just to remind you that next week we will have quiz. Quiz pukul berapa Pukul waktu ni juga pukul 11. Your questions maybe saya buat senang je. Calculate entropy, calculate conditional entropy. Make sure you understand which one to use, which one to formula nak guna, which formula that you need to use in your calculation. So your quiz will be 1 hour and 20 minutes. You have only 5 questions. So the question I will upload in the iTaklim, and then I will enable for you to download lah next week on Tuesday. Okay. Akan masuk for quiz 25%.
Wow.
Wah, banyak kan? 25%. Memang betul lah sebab tu satu je quiz yang ada. And then assignment, you have video assignment kan? Video assignment tu kalau boleh hantar by link je lah, hantar link. Tahu ke macam mana nak upload dalam your YouTube punya account?
Tahu.
Semua ada YouTube kan? Semua ada Google Meet?
Ada.
Okay. If senang bagi ni lah, bagi link je, saya boleh tengok daripada situ.
Nak kena hantar PDF-nya sekali ke tu?
PDF? Tak payahlah. Saya tengok your solution je daripada video. How you solve the questions from the video.
Okay. Individual kan?
Yes, individu. Dalam 2 ke 3 minit. Kalau cepat lagi bagus.
Okay.
Okay. Any more questions tak ada Okay, so if not, then I end this class with Assalamualaikum warahmatullahi taala wabarakatuh. Okay, you study until last week punya class, until Kolmogorov Sinai and generator. Yang hari ni punya tak masuk Okay, see you on Thursday. Assalamualaikum. Thank you class. Thursday. Thursday kita continue with invertible transformation. The same lecture.
Okay,
Lecture 13.
thank you Doctor.
Okay.
Okay, Doctor.
Okay, bye. Assalamualaikum.
Thank you, Doctor.
Assalamualaikum.
Welcome.